So, hello everyone to the final, sound joined. Yeah, the final deep learning theory seminar of the summer. One of the few is sparse in the summer and populated in the semester. Um, so we make an exceptional seminar for a pretty interesting speaker. So today we have Florian Frick. So Florian is a professor at CMU, Carnegie Mellon University, who I think has very interesting research. Works sort of applies geometric and like topological ideas, source and algebraic ideas, naturally. Um, we've like a bunch of problems all over this, I guess, computational geometry to everything. I think even you have some results in like graph coloring, like graphs and stuff like this. Um, so anyways, so Florian's results seem to be extremely relevant to at least one problem in the group, besides their own independent interests. So here we are. We have Florian today. And today we'll be speaking about the paper which like really got a lot of my attention, which is metric construction via optimal transport. Right. So after you, Florian, and thanks for coming.
Yeah, thank you. Thanks for this nice introduction. Thanks for having me. And yeah, so I was specifically requested to talk about this paper with this title, Metric Reconstruction via Optimal Transport, that seems to be relevant to something that people in the audience are interested in. So please feel free to interrupt me with questions. I've some idea of what I want to tell you, but you should get to give me direction in this talk. Ignore this number of slides that I have down there. I have no ambition to get through them. The full story will be told long before we get to the end of it. This joint work with Michael Hadamard and Henry Adams. I think I saw Henry join, so Henry will also feel free to interrupt if I talk nonsense or if there's something that needs to be, if you have any comments, anyone should feel free to just interrupt me. What's the general problem? The general problem that we want to address is the following. It's a reconstruction problem. We have a sample set S, and the set S was sampled from some underlying ground truth space X, perhaps with noise. Yeah, so here's some toy example picture of this, like a very, very densely sampled sample S with very, very little noise, uh, sampled from presumably a torus, right? The underlying space is presumably a torus here. For this problem to make sense, so we want to reconstruct X from just knowledge of S. Well, for this to make sense, we need to have some conditions. For example, S needs to be sufficiently dense in the sample space, right? If S only explores something on one side of X and nothing on the other side of X, we can't possibly reconstruct what X was. The space X has to be sufficiently nice. Of course, in the extreme case, you could always say, the space, the ground truth that S was sampled from is just S itself, right? So we want to have some niceness condition on X to say, oh no, it's actually this nice underlying torus, maybe that S was sampled from. Okay, so these are some conditions we need. And we should also, before diving into this, maybe briefly spend some time on what does it even mean to reconstruct this underlying space X from S? What do we mean by this? What things about X do we want to know, do we want to reconstruct? We could mean something very rigid. We could mean maybe we want to reconstruct all geometric information about X, right? X is some underlying, let's say, metric space, and really we want all the pairwise distances. That, of course, is very rigid. It might not even be meaningful, right? If you think of S as really a data sample set, and maybe it's in some high dimensional Euclidean space where some direction is maybe measuring time and some other direction is measuring some distance in feet, then actual distances won't be very meaningful, right? So maybe isometry is too rigid. Now, one complaint you might have is, wait, the title of your talk is metric reconstruction, so shouldn't you advertise that it is meaningful to reconstruct distances? Yeah, in some sense, but the metric reconstruction we're doing, yes, we're reconstructing the metric, but this is also, and let me put this at the beginning of the talk, this will also be useful if you're not interested in the actual underlying geometry. It's just that the metric we're imposing, the metric information we're using will be useful to reconstruct more qualitative information about the space X than, the metric itself. So more qualitative could mean something like you want to reconstruct it up to homeomorphisms or continuous topological type things about it, or maybe just homotopy types. Yeah, maybe you're just interested in, oh, there's a 5-dimensional hole in my space, something like that. Or, just algebraic signatures of that, like homology, maybe geometric signatures like curvature or dimension. Perhaps you're interested in equations that X satisfies as a subset of RD. All of this could mean reconstruction. Maybe the geometric things here are blue and the more topological things are red. Equations that X satisfies, that's something we have to be a little careful because it's very non-robust. If you have a bunch of points, a sample set, and it satisfies the equation, I don't know, x squared plus y squared is 1, and you just wiggle on one point a little bit, it's not true that it satisfies an equation that's almost x squared plus y squared is 1. Right? It's a very different equation. So we probably want to reconstruct more qualitative information. If we want to do this efficiently, we have to somehow exploit structure. We have to use something about the sample S to do this. And so some things that one might want to exploit in this are, how does S sit inside some ambient, maybe Euclidean space that it's just a subset of? Or how is S situated with respect to itself? What I mean by this is, so the first thing could mean, oh, S, there's some ball in Euclidean space over here, and S is very dense in it, or S is very sparse in it, right? That could be some information. And the second point here could mean something like, oh, if I look at this point in S, then there are many points at a small distance from it, right? So these are geometric and topological features of the sample that we want to exploit. Yeah, well, I indicated here we can think of geometric stuff as quantitative and topological stuff as more qualitative, right? Geometry cares about actual distances and angles, and topology just about, what is kind of close to something else. Okay, so that's a general problem I want to talk about. And so far, no objections. So let me give you some context. That's, of course, this has been explored in all kinds of ways, and I'm not claiming that I will now give you an exhaustive list of things that have been done there, but let me give you some flavor, some ideas, some things that people. So here, for example, 3 ways that are related to this reconstruction problem. One is a result from 1990 here, Peterson. If 2 spaces, and here we mean metric spaces, have finite covering dimensions, so they're finite dimensional in some sense, in some natural sense, and they satisfy a local contractibility condition, meaning for every point there's a neighborhood that I can just squish together, and they're close in this Gromov-Hausdorff sense. We can get into details later, but they're close in the metric sense, right? As metric spaces, they're close to each other. Then they're actually homotopy equivalent. Then they're topologically the same in this very, weak sense, right? So you could imagine that you have a sample and you want to show, oh, something, if I somehow thicken my sample to turn it into a contiguous space, then it is homotopy equivalent to some underlying space it was sampled from. And this Peterson result would give you a handle on cases where this might be true. Second example of this that I have here is Kaufmann and Lafont. They use diffusion maps, is what they call it. So it's random walks on the sample, and the random walk is weighted by just heat diffusion. And what this does for you is they can build a theory where the outcome is that this embeds the underlying manifold into a low-dimensional space. So it's some nonlinear dimension reduction thing, where you have the sample in high dimensions, you use this heat diffusion, these diffusion maps, and then this suddenly gives you the underlying manifold and represents it to you in a low-dimensional space. A third way, just to have a third option of what this might mean, Niyogi-Smale-Weinberger, if you have a uniform sample S in a compact manifold that's embedded into Euclidean space, then with high probability, the homology, so these algebraic signatures that count how many holes are in your space or in your data set, the homology of this underlying manifold is accurately recovered by taking the sample and just thickening it by epsilon. Just making it a little thicker, take the union of all these epsilon balls, and then that'll be roughly the correct shape. Okay. So for these three things, let me just, flash some pictures at you for them. So here, Peterson, if you wanted to use this for reconstruction of an underlying, let's say, manifold, in this case, maybe this was noisily sampled from a circle, or maybe was sampled from a very narrow annulus. If you want to use this result, what do you have to do? You have to take your sample and you have to somehow thicken it to get a continuous object, so that it might be locally contractible, so that local neighborhoods can be squished together. And then using this result, what you get if you thicken this up, well, maybe the result will be homotopy equivalent to the actual underlying manifold. In this case, you can see the circle. So you have to thicken the sample. That's
Just
the option.
one question. I mean, just sort of purely out of curiosity. When you do the like thickening in this in like Pearson's result, does it have to be like uniform across all samples, or can you like adaptively choose just to how much you thicken each sample just to get local contractibility?
So you want to adaptively choose what?
Yeah, no. So for example, I mean like this the thickening like radius, I guess. So if you have
Uh,
several samples in a small domain, like some part of the space and a few in the other, just wants
mhm.
to know if you should have like big balls on one side and small ones on the other, you know?
Ah, yeah, okay. Yeah, good question. In principle, you should probably do that, right? Because okay, I'm being very vague here, and we can nail down some details later, but of course, this has to be quantified. What does this mean? And this probably depends on the feature size of the underlying space that you want to reconstruct. So in principle, yes, you should adapt, what it means to thicken your sample for sure. But what the correct parameter is of course completely mysterious at this point. It's not clear how to do this, right? There's no practical thing that you can just do by reading this result.
Yeah, that makes sense.
Um, any other questions or maybe complaints at this point? Okay, good. For Koifman-Lafont for this diffusion map business, okay, I took this off Wikipedia. So you see there's a sample set. It looks circular, but it's embedded in a really weird way. It has like all these twists and so on. You run this diffusion map on it, and it'll embed this actual geometric circle for you into the plane. Right, so that's nice. You, of course, if you do this as a pre-processing step, you still have to recognize now this manifold. If it's a nice geometric circle in 2 dimensions, maybe you can just look at it. But if it's some manifold in 20 dimensions, you still need to have something to recognize this manifold, this space that you're reconstructing. We should, at this point, say, okay, what is the advantage of this? If we want to reconstruct an underlying manifold by using something like this as pre-processing, we can always assume that the underlying manifold is geometrically nice in some sense. It's something that really minimizes some energy. It's not something that has like little kinks or something. We can always, smooth it out using something like this as a pre-processing step. And for Niyogi
Ben,
Smale-Weinberger, okay,
can I
this
ask you
is
a quick question, if you don't
sure.
mind? Uh, just to make sure like the extra slides for me is extra. Yeah. So what do you mean by geometrically nice? And
Yeah,
like
what
in
do I
just a
mean by
tiny bit more detail, you know?
um, I guess it's not clear what I even mean by this. Uh, I'm not sure what the results are.
Okay,
If
okay,
we
no,
wanted
that's
to
fine.
have guarantees on, I have a sample in a high dimensional space, it secretly lives on a nice manifold. How close is the reconstructed manifold, geometrically to, I don't know what the precise
Okay.
results in that regime are.
That's fine,
So
fine. And yeah, no, I was just assuming some smoothness and some bounded curvature or something would, but I have no
that,
idea. You know?
no, neither do I. I'm not an
Okay.
expert on these
Cool. Me
diffusion
neither.
maps.
So cool.
Yeah,
Okay, cool.
but yeah, just giving you context. Yeah, sorry, I don't know what the
Oh, no,
precise
no, that's okay. It's okay.
quantitative estimates are in that regime. Okay. So for Niyogi Smir Weinberger, okay, here's a toy example picture, somehow a bunch of red points that were maybe sampled from this dotted circle that you see in the middle. And now if you grow, epsilon balls around these sample points, then you see the circle, right? Same problem in some sense as before. You still need to recognize, you now need to compute this algebraic invariant here. And question is, can you even do that? You can efficiently do that. What you do is you declare all these sample points to be vertices. You put edges whenever the corresponding epsilon balls intersect. Okay, I took a very dumb example here, but if three of the balls intersect in a common point, you put a triangle. If four of them intersect, you put a tetrahedron, and so on. That object that you get is called the nerve, and the homology of this is efficiently computable and is actually the same as the homology of the union of balls. So this thing, yes, you can actually compute this algebraic invariant, and it will, with high probability, recover the algebraic invariant of the underlying manifold. Let me complain just for the sake of complaining. There are two things that you could complain about here, namely, in principle, for every subset of sample points, you now need to check whether there is a point at distance less than epsilon from all of them, which in principle is inefficient because you have to iterate over all subsets if you don't exploit any additional structure. So it might be inefficient to just build this nerve to find out what this union is. The second complaint I have, this is not intrinsic. Somehow, maybe your sample, it's just embedded into RD for stupid reasons, and the points of Euclidean space don't actually have any meaning, right? And this is not intrinsic in the sense that we're trying to find a point in Euclidean space that's at distance at most epsilon or less than epsilon from a bunch of sample points. That's not intrinsic. It makes reference to the ambient space, which might not have meaning. So inefficient and not intrinsic. These are two downsides of this. Okay. So that's a little bit of context and a few complaints for all of them. Now, if I'm even a moderately skilled expositor, then the next slide will somehow say, oh, look at this magic tool that makes all my complaints go away. So here's the magic tool. It's a result by Latchev, 2001. Yeah, let's just try to read what it's saying in symbols and then unravel what that actually means. So if X is a closed Riemannian manifold, so satisfies some nice smooth equations, then the following is true. There's an epsilon naught such that for epsilon, so all this is just saying for sufficiently small epsilon. For sufficiently small epsilon, there exists a delta such that what? There's some construction that I can do with my sample set S, okay, do some construction at scale epsilon, then accurately recovers the homotopy of X. It tells you what this underlying space is, provided that the sample S is metrically close to the underlying space X. So there's the Gromov-Hausdorff distance here. It's a metrically close space to this underlying space. Okay, so that's what this is saying. Let me first tell you what is this? What is this object here? VR S epsilon is the Vietoris-Rips complex of the sample set S at scale epsilon. Again, this I took from Wikipedia. So what is it? It's the complex on vertex set S. You declare your sample set to be vertices again, as before, and now you fill in a phase whenever the corresponding sample points are pairwise at distance less than epsilon. Okay, so that's a little bit different than before because now we're only making reference to pairwise distances. Okay? So here's an example. The red points are a sample set. There's some epsilon. The epsilon is small enough that this point, this point, this point, this point, they're pairwise at distance less than epsilon. So here's a tetrahedron now that I filled in this Vietoris-Rips complex. Okay, so that's how this goes. Now, why does this somehow take care of my complaints? It takes care of my complaints because it takes the sample set S and it turns it into a locally contractible space. Now that's nice if you wanted to apply this Peterson result about if you're sufficiently close in Gromov-Hausdorff sense and you're locally contractible and finite dimensional in a certain sense, then you're homotopy equivalent. Why is it locally contractible? Well, around any point, if you look at a neighborhood of size, let's say epsilon over 2, well, then any 2 points in that neighborhood are pairwise at distance at most epsilon. You fill that in with a face, and you can always squish a face. Yeah, so it takes care of that. It is indeed intrinsic now. We don't make reference to points in the ambient space. We just say if the pairwise distance is less than epsilon, fill in the face. Okay, so nothing extrinsic anymore, it's intrinsic. Good. And lastly, it's more efficient. We don't have to iterate over all subsets because all the information is already contained in pairwise information, right? If the pairwise distance is less than epsilon, you fill in the face. So in principle, it turns some for the nerve, for Niogi, Smale, Weinberger, you would need the entire nerve. So you would need information about any subset, which might be exponential in the worst case. Whereas here, you just need information about 2-point subsets. So quadratic in the worst case.
I have one small question. Actually, one question I'm quite interested in. So for this kind of result, I guess 2001 was a long time ago. So since then, is there any guarantee that's you can handle a slightly more general subspace or basically metric spaces? This can actually be something more weird,
Generalize this.
Yeah. I mean, just out of pure curiosity,
Yeah. No, there has been work on this. Essentially, instead of a closed Riemannian manifold, what you really need, I mean, even if you just look at the proof from 2001, you see that proof probably applies a much greater generality. What you need is that your space is locally nice. It could just be an embedded cell complex or something where you have some control over the feature size. And I mean, nothing here is really quantified. And in the meantime, people have quantified some of these parameters, and there's really some, how large does the delta need to be, or how, at what stage do you actually get this equivalence, and so on. So
Cool.
Sushmaji has some work on that, for example.
Cool. Thanks. Hey, thanks.
Yeah, sure. Any other comments, questions at this stage?
Oh, go ahead, Rian. Don't be shy.
Hi. So, for this theorem above, is there any guarantee of the asymptotic distortion between this VR space and X? Can we guarantee that this asymptotic distortion is 1 as epsilon goes to 0?
I see. For small epsilon, is it actually true that this thing, I'm not sure what you mean by distortion. So this thing is a topological space.
Oh, this VR is, but there is a natural distance, natural metric on VR, right?
Good. Yeah, that's what we're getting to. Good. Okay. There is a natural metric on VR. If S is a super close sample and epsilon is tiny, yes, as S converges to X and epsilon converges to 0, metrically, this will be X. Now, what are the actual asymptotics of how it converges to X? It's a good question. I'm not sure I have an answer. It's a good question to ask. Yeah, I don't know what it is.
Thanks. Thank you.
Sure. Yeah, so what is this Lachev result saying? Let's try to unravel that a little more. So in words, right? For sufficiently small epsilon, we can sample this underlying space X densely enough such that this VR construction actually reconstructs X. Okay. And you guessed it, I have more complaints. A red but here. X is, of course, a priori unknown. We want to reconstruct X. We want to know what X is. So we have no access to X. We only have access to S. And we can't just sample more and more, right? We can't sample densely enough. S, the sample is fixed and given to us. And this result says, provided that S is sufficiently close to X, right? So we need to sample more and more to converge to X, but we can't do that. So all this result is saying is, if S is pretty close to X in a metric sense, then there are scale parameters such that at that scale parameter, this VR construction accurately reconstructs X. Yeah, so we want to turn this whole thing on its head. We have no idea what X is, so we can't just continue to sample more densely. So we have to find the correct epsilon here such that this happens. And now I can see two immediate approaches that you could have to this problem. One, I suspect, is more what someone trained in computer science would go for, and one is the less practical thing that a mathematician might go for. So what are these? You could either say, okay, if I need to find the correct epsilon where this happens, I could come up with some heuristics. There's some geometric parameters. I could maybe try to infer what the curvature is of S. I can, of course, compute the diameter of S. I can, these types of things. And based on these geometric information, based on these geometric features of the sample S, I have a heuristic for how to choose epsilon, and that's the epsilon I work with. Maybe there are a few epsilons. I reconstruct at those scales, and I hope to get the right underlying space X. That would be the heuristic approach. Mathematicians have the option of making their life easy and saying, okay, there's an ambiguity here, namely the choice of epsilon. And what I do is I just wrap this into a new object. I just say epsilon is now a parameter of a new object, which is epsilon maps to this VR construction S comma epsilon. So I just reconstruct for every epsilon whatsoever. And now I have a spectrum of VR complexes. For every epsilon, I have one, of course, completely uncomputable, but I could, in principle, say that and say, and now this is my object that I use to witness reconstruction. Let's talk about the second approach. I'm a mathematician, so obviously I like this approach, even if at first sight it's completely impractical. So let's see where this leads us. First, well, just having a whole spectrum of, let's say, topological spaces or simplicial complexes is very unwieldy. And of course, what we do is we throw this homology functor on there. So maybe instead of a bunch of homotopy types, we now get a bunch of vector spaces. So this is, for every epsilon, we get a sequence of vector spaces. This is what people call persistent homology. This can be efficiently not only computed, but also represented for every fixed epsilon. So these homology groups of vector spaces, they have generators, and you can record when their birth time is and when their death time is. So maybe there's a 5-dimensional hole in your space that appears at time 2, and at time 7, this 5-dimensional hole gets filled in as the epsilon grows, right? And you can just efficiently record this information in something called a persistence diagram. And now there's good news. Finally, some good news. This thing is stable. If I have two sample spaces, S1 and S2, and they're pretty close to each other, and I compute this algebraic information about them, then the persistence diagrams that I get, in a certain natural sense, are close to each other. In particular, that means if my sample S is pretty close to my underlying ground truth X, then the persistent homology of S and the persistent homology of X, the underlying space, are pretty close to each other. Yeah? So if S is close to X, then this algebraic witness of what S is pretty close in a natural sense to this algebraic witness of the underlying space X itself. So in some sense, okay, there's a beautiful workaround, right? We have to choose epsilon. No, we don't. We just wrap it into a new object, parametrized by epsilon. And these new objects, they're actually close. If S and X were close, then the algebraic information is close. So, question.
Yeah, I have one question, but I'm not sure exactly how to formulate it. I guess that's okay.
That's fine.
Yeah, so is there like a reasonable sense to think of yeah, I guess this parameterization of this map is in some sense being continuous, like at least okay, in the sense that you take like a specific like level of like this homology like complex, whatever, like H2 or something, and you look at dimension, like simple information. Like, is there any way to like think of this as depending in some way continuously on epsilon? I mean, obviously the dimensions will shift, when epsilon gets bigger or
Uh,
smaller. But is there any like meaningful way? The reason I ask is because then I can imagine someone doing some kind of like binary search algorithm.
Yeah, I think there is a reasonable sense in which this continuously depends on epsilon. Yes, that's true. If you, yes, um, for every, what can we do? Uh, it's of course discrete in the sense that at some, I think of epsilon as time. So epsilon
Yeah.
grows from zero, and then, as time passes and as I get a denser and denser Vietoris-Rips construction, at
Yeah,
some point, certain things will either appear or disappear.
exactly. It's continuous, I guess, but I don't know.
So there's some jump in that, right? But maybe, I guess you should think of things that just appeared as they have very little weight because they literally just appeared, right? And if you're willing to wait in that sense, then yes, this would be continuous in epsilon.
Okay, that's cool. That's cool. Thanks.
Sure. So good, right? Beautiful workaround. All that's left to do is for many template spaces X, for many manifolds, we can always think of them as very smooth and smoothed out by just pre-processing with diffusion maps or something. But for many of these templates X, we just need to compute the persistent homology to have a library of those so that when you have a sample, you compute this at a bunch of epsilons, and then you compare it to your library, and you just find the correct X, and you say, oh, that's the underlying space. So it's a nice workaround in that sense. And of course, well, that's just how this talk goes. I have more complaints, namely, we actually don't know the persistent homology of that many template spaces X. This seems to be really difficult. So my co-authors, Michael Adamaszek, Henry Adams, they computed this not that long ago for the circle, right? This is maybe the first manifold space where you would want to know what is actually the persistent homology of this continuous object to compare to what you get from a sample. And what they showed is VR S1 epsilon takes on the following homotopy types. It's a circle, then a 3-sphere, then a 5-sphere, then a 7-sphere, and so on. And at what epsilons do these changes of homotopy type occur? They occur at the diameter of an inscribed regular triangle, pentagon, heptagon, and so on. So that's the circle. For general manifold X, computing the persistent homology here seems really difficult. For small epsilon, we have a result of Hausmann that the VR construction of X and small epsilon reconstructs X as you would expect, right? That should be the thing that happens. But if this is to work, what we want to make work here, namely, we want to have information about VR X epsilon at larger scales epsilon, because we don't know what small scale epsilon even is, right? If you just have access to the same. So the challenge is this VR complex of X at epsilon. It's a simplicial complex, so it's a combinatorial object, but X is an underlying manifold, so it has uncountably many vertices. It's not something that you can give to a computer to do something with, right? And it retains geometric information about X only in this combinatorial form of filling in faces if you're pairwise at distance epsilon. Yeah, so it's a very unwieldy large object that you can't easily study. And that's where metric reconstruction comes in. Let's remember a metric on X and enforce this metric on this Rips complex, because maybe then we have access to analytical tools where we can actually compute these homotopy types and build a library of persistent homology of underlying manifolds to compare our persistent homology of samples against. So retain metric information, and this gives access to tools of metric geometry. And how do you do this? So here's one way. There are various ways of doing this. Here's one way of doing it. This maybe goes back to something that was suggested by Misha Gromov. So what do? You have a compact metric space X, and you now define a spectrum of metric spaces. For every epsilon, you have a new metric space X epsilon, and maybe I'd like you to think of X epsilon as X, but a little thicker. You thicken X, right? As epsilon grows, it gets thicker and thicker and thicker. And what is it specifically? Well, X sub epsilon consists of probability measures on the space X whose support has diameter less than epsilon. So it's only supported in a small diameter set. So it's a space of fuzzy points. Every point can now be spread out a little bit as long as the diameter, as long as pairwise the distance between points in the support is less than epsilon. And okay, you could also say less or equal to epsilon. I'm introducing this here just for, to make some statements easier later on. And okay, so that's a set, but the set has a metric, namely an optimal transport metric. It's probability measures, and I can measure, how far these probability measures are apart. So for example, here you have a red probability measure and a blue probability measure. And how far are these apart? What's the correct metric to put on these? Well, you could say, well, I just measure how much work it takes to transport the red set to the blue set. So maybe in this example, you would take 1/3 of weight from here and transport it over here. So that's already at the correct position. And then the other, what is it, 1/6 or so, you transport over here maybe. And then some of this goes here. This mostly goes here and splits here, and some of this goes there. And maybe that would be an optimal way of transporting the red mass to the blue mass. And the amount of work that it takes to do that that's our metric. That's the metric we put on. So in symbols, if you have two probability measures, here's what you do. You infimize over probability measures pi on x times x, where pi has marginals mu1 and mu2. So if you project to x1, if you project to the first coordinate, it's mu1. If you project to the second coordinate, it's mu2. And then you just integrate over the distance of all pairs of points, right, with respect to that. So that might mean something to you, or it might, maybe you like the explanation more of, it measures the work of transforming mu1 into mu2. The space X itself can be identified with Dirac measures that are fully supported in just one point. Every point X corresponds to the Dirac measure that gives weight 1 to exactly that point. And then in this definition, the distance between Dirac measures is just the distance in the underlying space. So yes, this preserves metric information about the space X. It's the same metric as X embeds into this space of probability measures, this metric thickening.
And so just I guess a question / comment, more on, that's just to check, So basically what you're saying is that like this, I think you're calling it S, like their sample subset of X, So essentially you're embedding this, asymmetrically is finitely supported measures, which are like, have the additional condition that they're sufficiently close, like the points, I guess. There's going to be mass between them kind of thing, right? Is that right?
Right. So the space X itself is even just measures that are fully supported in a single point, right? And then if if you make this a little bit fuzzy, if you say, okay, now you can be supported in a tiny little neighborhood, right?
Yeah.
Then yes, you get a space that's a slightly thickened version, right? Because now the points are fuzzy.
Yeah.
You know, so your space is a little thicker, right?
Hmm. Yeah, that makes sense. Makes sense.
Okay. Okay, if we're happy with that, let me give you a few results about this. So first of all, this works in some sense. So with Henry Adams and Giga-Wirth, we proved if X is a compact metric space and it works in greater generality, then this Vietoris-Rips construction that was relevant in Latchev's result, and this metric thickening construction that first of all maybe has nothing to do. I mean, it's inspired, of course, by this, but we somehow forcefully defined a metric, right, on this object by using optimal transport to measure how far apart points are and how far apart measures are. But these two objects, they have the same persistence diagrams. Yeah, this algebraic witness is the same. They even have isomorphic homotopy groups, which is more refined information. And Patrick Gillespie showed that they're even weakly homotopy.
I feel like just to return to like the last question, I feel like I didn't express it in any in any reasonable way. I guess what I meant to ask was rather, so if you have like your sample, your net or your sufficiently like sample subset, S, yeah, I guess what I meant to articulate, which I didn't, was that this VR x epsilon, like when you realize it as these probability measures, so am I correct in understanding that it's a subspace of the, say, Wasserstein space on uh on S, So
Yes.
yes, yeah, that's what I meant to say.
Correct. Yes.
Okay,
It
cool,
is
cool.
right. It's a filtration of the Wasserstein space on S, and
Yeah, okay.
it's the filtration is what? It just the diameter of supports grows from
Yeah.
0, where you get the space X, to any diameter is allowed, where you get the whole contractible Wasserstein space.
Yeah, okay.
Right?
So yeah.
And as you grow in the space, the persistence that you get from that is the same as the usual Vietoris-Rips persistence.
Okay, perfect, cool. Yeah, thanks actually. Yeah.
Great. Other questions, comments? Okay. So yeah, this was this weird, unwieldy object that we had to compute to get a library of underlying templates and their persistent homology. This seems very difficult. This is saying instead you can compute this, which is amenable to analytical tools. You can use geometric tools. Yeah, it's not just a combinatorial object. It retains analytical information about your space, so you can use new tools to understand it.
Can I ask a follow-up question? So this is I think precisely like one of the points that we're quite curious about,
Uh-huh.
amongst there's many cool things. Um, right. So is it like if you now kind of completely opposite to the first thing I asked, if one has a tiny bit more structure on X, or I don't know, is it possible to strengthen that result so that these two things are more than just homotopy like equivalent? Like they're like maybe homomorphic something? Because the reason I ask is we're hoping to push one of the metrics, like the metric you have on VR, on onto onto X somehow and use that just to make a comment. But yeah, is it
Good.
ever
Yeah,
possible to strengthen this?
good question. Yeah, it's a good question. Um,
I don't know if it's a good
it
question.
is
It's a
it
hope.
is true. It is true that these things are not just homotopy equivalent. Well, I guess I'm just claiming that they have isomorphic homotopy groups, which is a little bit less,
Mhm.
but that they're metrically close in a Gromov-Hausdorff sense. Yeah, so as metric
Mhm.
spaces, they are close. And now, does that mean that I can take a metric on the thickening of S of the sample and push it onto X? That was part of the question?
Yeah, exactly,
That's
exactly.
that's an interesting question that I'm not sure I've thought about it. That's an interesting question to ask. Yeah, can I somehow push this forward onto X, right? Or is it
Yeah, basically.
Right. Um, I mean, in some sense, I should expect that X embeds into this space. But to really recover the metric on X itself, it's an interesting question. I shouldn't speculate. Well,
I don't know.
this is,
No, you have each other's emails, no reason to do it on the fly,
yeah.
Um, but okay, maybe just like a follow-up question that's not related, but just to make sure like the whole picture is being digested in my one coffee brain.
Uh-huh.
Um, okay, so if you put this with the early result you mentioned by I think Hausmann you said, so then you can kind of conclude that VR X epsilon has the same homotopy type, like homotopy groups as X.
Uh-huh.
I guess is that like
Uh-huh.
correct or no?
That's correct. Yes.
Yeah,
Uh,
okay. I thought
yeah.
so, but just wanted to be
Good.
a bazillion
Good.
percent
Yeah.
sure about everything. Okay, cool. Thanks. Oh,
Good. Great. Yeah. Of course. Good. Okay. So now, I guess, at the very least, in my last 2 or so minutes, I should convince you that, this is not just some theory, but it was good for something. So let me flash something at you where it was good for something. Here's a picture of S1. Okay, so here's the circle. And as you thicken it, here's a probability measure. Yeah, maybe this is the diameter of the support, the length of this edge. So you can think of this thickened space as an annulus now. And as this grows, this epsilon, you fill in more and more of this disk until the hole in the middle disappears. Where does the hole in the middle disappear? Well, exactly once you can inscribe this equilateral triangle. So if this has the geodesic metric where the circumference is 2 pi, then this happens at 2 pi over 3. So up until this scale, you get an annulus, which you can push out to the circle. So topologically, you're still the circle. But then at this point, the homotopy type pops up. At this point, you suddenly get a circle's worth of these triangles. So a circle's worth of filled-in triangles, that's a solid torus. You have this triangle and a circle worth of them, so that's a nice thick torus. And this torus you now have to glue into this space. If you keep track of how to do this, then you see, oh, you get this thicker and thicker S1, and then you have to glue in a torus of regular triangles, and you get a three-sphere actually. So that's what this is doing. And this somehow is the general picture for spheres. If you have a d-dimensional sphere with a round metric, so you measure length via geodesics on the sphere, for small epsilon, actually for quite a while, what you get is that this thickening of the sphere or the Rips complex of the sphere, whatever you prefer, is homotopy equivalent to the sphere itself. Namely, well, you thicken, it's still the sphere, but thicker, up until the point where you fill in the hole in the middle, there something new happens. Where do you fill in the hole in the middle? It's at the diameter of an inscribed regular d+1 simplex. Now, for the circle, it was a triangle. For a two-sphere, you want to inscribe a regular tetrahedron, and the edge length is where something new happens. And what is this new thing? Well, using this theory, we can compute the next homotopy type, right? And it's just, okay, here's a representation of what it is. It is the d-sphere join. What join means is take abstract convex combinations with. And what do you take abstract convex combinations with? This, whatever this means, but it's a space of regular simplices. So you have to glue in the space of regular simplices, and that's the next homotopy type. That's the next thing that happens. And in general, what you should expect happens as this parameter grows is, well, the next thing that you have to glue in is what is the next set on the sphere that is not robust with respect to perturbations whose diameter. So what's the interesting thing about an inscribed regular tetrahedron in the two-sphere? If you wiggle on the vertices a little bit, the diameter only goes up. And that's why this is a new phenomenon, right? As this parameter increases, suddenly at this scale, there's a new phenomenon. What I'm saying is the next scale where you will see a new phenomenon, morally, what you should expect is it's a set of larger diameter that has the property that if you wiggle on the points a little bit, the diameter only goes up. And then you have to, glue in this space of, this set up to symmetries. That's morally what's happening. Or maybe I'll just flash one or two slides at you with related work, like what have people done? Well, you can get homotopical connectivity bounds. So the first so and so many homotopy groups vanish as epsilon grows. You can do something about equivariant topology of these spaces. You can even compute persistent equivariant cohomology, at least in the case of the circle. This, of course, means there are various connections of Vietoris-Rips complexes and metric thickenings to quantitative topology, metric geometry. People have explored this, like bounds for Gromov-Hausdorff distances, Lim-Mimoli-Smith, and then Facundo-Mimoli, Henry Adams, and I, and then many co-authors have a paper on this. It's related to the filling radius of a manifold. It's related to coverings and packings, Borsuk-Ulam type results. So there's all kinds of math that you can do with this in the end. But I think that's the story roughly that I wanted to tell. So at this point, let me say thank you, and I'll stop here, and I'm happy to answer any questions or if you have comments.
Oh, thank you very much for the really interesting talk.
Thanks.
Maybe I have one last question, actually, which happens to be related to the second point here. Yeah, it's more like a vague thought, but slash question. So actually, I think in one of these, like, I think is it the first paper that Gromov have like introduced this filling radius, like this systolic inequalities paper? He creates like these bi-Lifshitz embeddings of these like manifolds of reasonable curvature into low-dimensional space by just looking at distances to like a set of points, like an S kind of, like your sample kind of thing, And if S is sufficiently small, it's given by some systole, like systolic upper bound, like systole divided by 10 or something. Then this thing is a bi-Lifshitz embedding, So somehow it preserves some like geometric information, but a bit less in isometry, like you said in the first slide, And of course, you know what that is, just saying for anyone else in the audience. Yeah, so I guess my question is somehow, is there any relationship between like those kind of ideas? And maybe you can say a bit more about this filling radius point, Yeah, it seems quite relevant or potentially very related to that,
Yeah, let me see. I can probably say something about this, although
If you don't
who
mind.
knows if I can order my thoughts sufficiently well to actually say something that makes sense.
Well, I tried, but this is the best I can do.
So there is this related construction of the tight span of a metric space. And the tight span of a metric space is, so it's the smallest hyperconvex metric space that the metric space embeds into, meaning if a bunch of metric balls pairwise intersect, they must all intersect. And in this tight span, there's a filtration. And this filtration, if you look at this filtration, it's the same thing as the Vietoris-Rips complex or the same thing as these metric thickenings. And that's essentially what you see in that theory that, in this tight span picture, there's some scale where you fill in the whole thing, and that's exactly the filling radius, right? The filling radius is where you can read it off the Rips complex. Now, yeah, what can I actually say concretely about this? So yes, I guess the one thing you can concretely say about this, you can read off the filling radius from the Rips complex, and this theory goes via this tight span.
I see. Yeah, okay, cool. Okay, cool. Any other questions in the audience? Yeah, I guess it's still mathematicians and summer, so it's like two levels of abstractions to questions, both introversion and heat. Anyways, I thought that the talk's very interesting, and yeah, maybe I'll reach out to you with some like more precise questions about what we're thinking about. But I think
Yeah, great.
if I can just say, like, if you ever have any thoughts about this homomorphism like question asked, I'd be super interested, actually.
Okay, great.
Yeah, cool. And yeah, thanks again. Like
Yeah,
Florian
thanks
for
for
the
having
really
me.
nice talk. Yeah, and I'll see it on YouTube soon, I guess.
Okay. Thanks very
All right.
much. Okay.